Let's continue with the back page of 1/4 through 3/5 morning review on limits. Number 3, determine the horizontal asymptotes. So if we're asked to determine the horizontal asymptotes of something that looks like this, where we have numerator over denominator and denominator has a radical, this is an indication that there could be two separate horizontal asymptotes. And we could end up having a graph that looks something like this, where as we approach negative infinity, the graph is leveling off at a different y value than if we approach positive infinity. So what we need to do is we need to test the limits as x approaches infinity and negative infinity separately for these expressions, because for the function, because we may get different values. So let's do one at a time here. So as we approach positive infinity, we're going to just take it as it is. We just look and see that the numerator and denominator share the same degree. And if they share the same degree, we simply take the leading coefficients, meaning that the 15 and the negative 23 is going to be irrelevant. So leading coefficient is simply going to be negative 4 over the cube root of 5. So that's where the graph is going to level off as we approach positive infinity. So the graph is more something like this. Okay, let's approach the negative value as we approach to the right of the graph. As we approach negative infinity, we do the same thing, except we have to adjust for the fact that there is a negative in front of here. So we're going to have to include a negative in front of the cube root, and this will cancel out to be positive 4 over cube root of 5. So essentially, we're just getting the positive and negative version of the same value, but they will end up on the graph being separate horizontal asymptotes. All right, number 4, step through continuity conditions. If not continuous, show work to determine the type of discontinuity. All right, so there's 3 parts to this piecewise function. We have a branch that exists to the right of negative 4. We have a branch that exists to the left of negative 4. And then we also have an equation that just represents a specific point at negative 4. So all this is centered around negative 4. We just want to know, do these 2 branches in the ordered pair, do they connect at negative 4, allowing the function to be continuous? So let's just step through our continuity conditions. First is, does the ordered pair exist at negative 4? So negative 4, the graph exists with the middle equation here. So plug negative 4 into the function. So 4 times 4 minus 1. Sorry, 4 times negative 4 minus 1. So negative 16 minus 1 is negative 17. So we know the ordered pair on the graph at negative 4 is negative 17. Okay, next thing we're going to do is test the one-side limit. We have a branch that exists to the right of negative 4. We have a branch to the left of negative 4. We just want to know, do they connect at the same y value? So we're going to find the limit as x approaches negative 4 from the right side of negative 4 for this expression. So that's the bottom one here. And then we're also going to evaluate the limit as x approaches negative 4 from the left side of negative 4. We know whether we're pushing from the left or from the right side looking at our inequality here. So less than negative 4 means we're approaching from the left side of negative 4, 5x minus 1 over 2x. So when we evaluate the one-side limits, the first thing we always do is we just plug in out to evaluate algebraically. We just plug in the x value and we disregard the one-side limit for now. Okay, so plug negative 4 in for x. So 5 times negative 4 is negative 20 minus 1 is negative 21 over negative 8. Negative 21 over negative 8 is a real number, so 21 over 8, which means that this is our one-side limit, that we don't have to worry about the negative from the left side of negative 4. As long as we get a real number, then that will agree with if we were to plug in, let's say, negative 4.1. The only time we have to worry about this negative or the positive one-side limit is if we get does not exist, and that forces us to have to determine whether the graph is approaching positive or negative infinity. Then we look at evaluating further using decimals. All right, so if we're approaching negative 4 from the right side of negative 4, we are dealing with this expression. So plug negative 4 in for x, we get negative 2 times negative 4, which is 8 plus 5. I'm sorry, 8 plus 5, negative 4 times negative 2 is 8 plus 3, which is 11. So this should be positive 11, not negative 5, because we're plugging negative 4 into the x. Now notice that these one-side limits do not agree, and because they don't agree, we know there's a disconnect. We know this is going to be a jump discontinuity, a non-removable discontinuity. So therefore, we know that the limit does, since limit doesn't exist, the function is not continuous because the second condition fails. All right, part B, we have a piecewise function, but this is going to be a little bit different. Here, we see the graph is going to exist everywhere on the left side and on the right side of negative 2, all contained within this function. It's, the two branches on either side of negative 2 is not split between two piecewise functions. It's all self-contained within one piecewise function. The only thing that's different is that the graph doesn't exist at negative 2 for this piecewise, and it's getting filled in by this other piecewise function at this order pair negative 2. And the question is, does this point fill in the hole for this graph? If it fills in the hole for the graph, then we know the function will be a nice continuous function. But if the point exists elsewhere where the hole exists, then we know that it's going to be a removable discontinuity. All right, so first things, first we need to determine where the order pair is. So g of negative 2 is for the second piecewise, so plug negative 2 in for x, we get negative 6 plus 2, which is negative 4. We're going to evaluate the limits. We know that everything is self-contained within the first piecewise, so we can just jump directly to evaluating the limit as x approaches negative 2. There's no need to do one-sided limit since we're not dealing with two separate branches of the graph. All right, so we're evaluating x approaches negative 2. So if we plug negative 2 in, we get 0 over 0, which tells us to keep going further in terms of algebraic reduction. So we can expand the numerator. We get x plus 2 times x minus 2 going through difference of squares. Divide by x plus 2. Notice the two factors of x plus 2 reduces and cancels out. We're left with x minus 2. So we reevaluate, plug in negative 2 in for x. Negative 2 minus 2 is negative 4. So the limit exists at negative 4. The order pair exists at negative 4. The third condition is asking, do the first two conditions match? Negative 4 and negative 4, they both agree at the same y value. So the point exists, the limit exists, and then the point is going to fill in where the hole is for the first graph. So we know the function will be continuous. All three conditions pass. Our function is continuous at x equals negative 2. All right, last part here. Answer the following questions for the piecewise defined function. So we're answering these questions based off of this piecewise function. So here we have three separate branches. We have a graph that exists to the left of negative 2. We have a graph that exists between negative 1 and 2. And then we have another graph that exists to the right of 2. So three separate branches, and then they may or may not connect at these endpoints. All right, so f of negative 3 over 2. So f of negative 3 over 2, which is negative 1.5. So negative 1.5, we know that the graph is only going to exist to the left of negative 2, and then there's a break, and then there's a break from negative 2 to negative 1 where the graph is not going to exist. So the graph is not going to connect. There's a big gap. There's a gap between negative 2 and negative 1. So the graph doesn't exist, since nowhere between these branches is this order pair covered, or this x value covered. Part B, f of 2. So f of 2 is with the third piecewise. It's not defined for the second piecewise. It is defined for the third one. So we just plug 2 into the third piecewise. So 3 times 2 is 6. 6 minus 2 is 4. So that's our order pair. F of 1. Looks like f of 1 will be for the second piecewise. So if I plug 1 in, I get 1 plus 6, which is 7. 7 over over 1 minus 1 is 0. So 7 over 0, we know that that point does not exist. It must be a vertical asymptote. Does not exist. Okay, limit as x approaches negative 2 of f of t. So as we approach negative 2, we know that the graph is going to exist to the left of negative 2, but then immediately to the right of negative 2, the graph is not going to exist because this piecewise function there's going to be a complete break between negative 2 and positive 1, and so we know the limit can never exist at an endpoint, so limit does not exist. Right. In order for a limit to exist, the graph has to approach the same y value from either side of 2. The graph approaches positive 4 from the left side, but then from the right side, there's nothing to the left of approaching negative 2 from the right side. All right. As we approach negative 1 from the right side of negative 1, so here's negative 1 from the right side of negative 1. We're talking about this piecewise function, so we just have to what we can do is we can plug negative 1 in. So if we plug negative 1 into this function here, we just wanted to test the one side limit here. So we plug negative 1 in, we get negative 1 plus 6, which is 5, and then negative 1, which is 1. 1 plus 1 is 2, so 5 halves. We see the limit, one side limit exists at 5 over 2. Okay, limit as x approaches 2, so limit as x approaches 2, that means we have to test the one side limit. So we're going to approach 2 from the left side of 2, and we're going to approach 2 from the right side of 2. So I'm showing the work here. From the left side of 2, we're going to use the second piecewise. From the right side of 2, we're going to use the third piecewise. Plug 2 in, we're going to get 8 over 2, which is 4. Plug 2 in, third piecewise, we get 3 times 2, 6 minus 2, which is 4. So 4 equals 4. The limit does exist because the one side limits agree, so therefore our answer is 4. Okay, part G. Okay, as we approach 0, we're talking about this piecewise. So if we plug 0 in, we'll get 0 plus 6 over 0 minus 0. 6 over 0 is undefined, so therefore it does not exist. Okay, as we approach 0 from the left side of 0, so if we approach from the left side of 0, we know that there's a vertical asymptote there, so all we need to do is we just have to decide if we're approaching an asymptote, it's either going to go to positive or negative infinity. So we can just test a decimal. This is where we have to evaluate using decimal. So 0 from the left side of 0 would be an example, would be a representative decimal could be negative 0.1, okay, from the left side of 0. So if we plug negative 0.1 into the t values here, all we care about is whether the numerator and denominator gives us positive or negative values. And then from there we can determine, there's only two options, either positive or negative infinity. So we plug negative 0.1 into our t value. Negative 0.1 plus 6 is a positive value. And then negative 0.1 squared minus negative 0.1, this will be also positive value, so positive over positive. We know that as the graph approaches 0 from the left side of 0, the graph is going to shoot up to positive infinity.